Chapter 2, Unit 2, Data. 2.1, Binary Numbers and Place Value. Why computers don't count like us? Let's start with a question that sounds almost too simple. Why do computers use binary? You use 10 fingers, so humans naturally invented a base 10 number system, the decimal system. A computer at its core is built from billions of tiny electrical switches. Each switch is either on or off. There's no kinda on, that physical reality. Two possible states is exactly why binary, the base 2 number system, is the native language of every computer ever built. When you understand that, binary stops feeling arbitrary and starts feeling inevitable. The College Board wants you to internalize this connection. The reason computers use binary isn't a historical accident or an engineer's quirk. It's because binary maps perfectly onto the two physical states of electronic components. That conceptual link alone has shown up on multiple choice questions, so keep it close. Place value, the engine behind every number system. Here's the key insight that unlocks both decimal and binary at the same time. In any number system, place value is everything. In base 10, every position in a number represents a power of 10. Starting from the rightmost digit and moving left, you have the ones place, 10 to the 0 power, which equals 1, the tens place, 10 to the first power, the hundreds place, 10 to the second power, and so on. The digit in each position tells you how many of that power of 10 you have. Binary works identically, just swap out 10 for 2. Starting from the rightmost position, you have the ones place, 2 to the 0, which is 1, then the twos place, 2 to the first, then the fours place, 2 to the second, then the eights place, 2 to the third, then 16s, 32s, 64s, 128s, and so on. Each position is exactly double the one to its right. The digit in each position is always either 0 or 1. You either have that power of 2 contributing to your total, or you don't. Think of it like light switches in a row. Each switch controls a lamp of a specific wattage. The rightmost lamp is 1 watt, the next is 2 watts, then 4, 8, 16, and so on. A binary number is just a record of which lamps are on. The total wattage is your decimal value. Converting binary to decimal. The formula you need is this. To convert a binary number to decimal, multiply each binary digit, called a bit, by its corresponding power of 2, then add all those products together. Let's walk through an example with the binary number 1101. Working right to left, you have a 1 in the ones place contributes 1, a 0 in the twos place contributes 0, a 1 in the fours place contributes 4, and a 1 in the eights place contributes 8. Add them up, 8 plus 4 plus 0 plus 1 equals 13. So 1101 in binary equals 13 in decimal. Practice this until it feels automatic, because the AP exam will absolutely ask you to perform this conversion. A diagram worth committing to memory is a simple place value table. Draw a row of boxes. Label each box with its power of 2 above it, starting with 2 to the 0 on the right and increasing as you move left, and then write the corresponding decimal value of that power below. When you're given a binary number, drop each bit into the appropriate box and sum only the boxes containing a 1. This visual tool is something you can recreate on scratch paper during the exam in under 30 seconds. Converting decimal to binary, going the other direction, decimal to binary, uses a method called repeated division. Take your decimal number and divide it by 2, record the remainder, which will be either 0 or 1, take the quotient and divide by 2 again, record the remainder. Keep going until your quotient reaches 0. Now read the remainders from bottom to top, and that sequence is your binary number. Try it with 13 divided by 2 is 6, remainder 1. 6 divided by 2 is 3, remainder 0. 3 divided by 2 is 1, remainder 1. 1 divided by 2 is 0, remainder 1. Reading remainders from bottom to top, 1, 1, 0, 1, or 1101. You're back where you started. This method is reliable and systematic, and it's the one College Board rewards in free response scoring rubrics when students show their work. Bits, the number of values, and an essential formula. A single binary digit is called a bit. This is AP-specific vocabulary. Use it. A group of 8 bits is a byte. Here's a formula you must memorize. With n bits, you can represent exactly 2 to the n distinct values. 1 bit gives you 2 values, 0 and 1. 2 bits give you 4 values, 0, 0, 1, 10, 11. 8 bits give you 256 values. This formula appears constantly on the exam, often in questions about data storage or the limits of representation. The edge case that trips up students every single time is the question of the maximum value versus the number of values. With 8 bits, you can represent 256 different values, but those values range from 0 to 255, not 0 to 256. The maximum value is always 2 to the n minus 1, because 0 takes up one of those slots. Don't let the exam catch you writing 256 as a maximum 8-bit value. It won't be. The answer is 255. Common MCQ, traps to dodge. One classic trap presents you with a binary number and asks for its decimal equivalent, but reverses the bit order in the answer choices. Always anchor yourself to the rightmost bit as the ones place. Direction matters. Another trap asks, what happens when you add one more bit to a binary representation? Students often say you can store one more value, but the correct answer is that you can store double the number of values. Each additional bit doubles the representational capacity, because 2 to the n doubles every time n increases by 1. Connections to the rest of the course. This section is foundational to virtually everything that follows in Unit 2. When you study data compression, you're asking how to represent information in fewer bits. When you explore the limits of data representation, like why floating point arithmetic sometimes produces small errors, binary place value is the root explanation. In Unit 4 and Unit 5, when you encounter algorithms that use bitwise operations, or when you analyze how data is stored and transmitted across the internet, the vocabulary and logic you built here are doing the heavy lifting underneath. Binary isn't just a topic to learn, it's the conceptual infrastructure of the entire course. With a solid grip on how binary place value works, you're perfectly set up to explore how computers represent not just whole numbers, but all kinds of data, from colors to text to sound, which is exactly where we're headed next. 2.2 Number bases and conversions. Binary, decimal, hexadecimal. Why number bases matter. Let's start with a question you've probably never thought to ask. Why do we count the way we do? When you hit the number 9 and add one more, you carry over and write 10. That's not some law of nature, that's a human convention, almost certainly because we have 10 fingers. Computers, though, don't have fingers. They have transistors, and a transistor has exactly 2 states, on or off. That's it. So computers count in 2s, not 10s. Everything you'll ever do in AP Computer Science Principles, storing images, streaming music, sending a text, ultimately comes down to sequences of ons and offs, ones and zeros. Understanding number bases isn't just trivia for the exam, it's the foundation of how digital information actually works. Decimal, the system you already know. Your familiar counting system is called base 10, or decimal. The word decimal comes from the Latin for 10, and the whole system works by place value and powers of 10. Take the number 347. The 7 is in the 1's place, that's 10 to the 0 power, which equals 1. The 4 is in the 10's place, 10 to the 1st power. The 3 is in the 100's place, 10 to the 2nd power. So 347 really means 3 times 100, plus 4 times 10, plus 7 times 1. This expand by place value method is something you already do intuitively, but writing it out explicitly is the key skill you'll transfer to every other number base. Get comfortable with this notation because you'll use it constantly. Binary, the language of computers. Binary is base 2, which means only 2 digits exist, 0 and 1. Each digit in a binary number is called a bit, short for binary digit. Place values in binary work exactly like decimal, except instead of powers of 10, you use powers of 2. Starting from the right, 2 to the 0 is 1, 2 to the 1st is 2, 2 to the 2nd is 4, 2 to the 3rd is 8, 2 to the 4th is 16, 2 to the 5th is 32, 2 to the 6th is 64, 2 to the 7th is 128. Memorize those 8 values. They appear constantly on the AP exam. Converting binary to decimal is straightforward. Take the binary number 111. Write out the place values from right to left, 1, 2, 4, 8. Now multiply each bit by its place value and add. 1 times 1 is 1, 1 times 2 is 2, 0 times 4 is 0, 1 times 8 is 8. Add them up. 1 plus 2 plus 0 plus 8 equals 11. That's all there is to it. Going the other direction, decimal to binary, requires a different approach called repeated division. Take your decimal number, divide by 2, and record the remainder. Divide the quotient by 2 again. Record the remainder. Keep going until the quotient is 0. Then read the remainders from bottom to top, and that's your binary number. Let's convert 13 to binary. 13 divided by 2 is 6 remainder 1. 6 divided by 2 is 3 remainder 0. 3 divided by 2 is 1 remainder 1. 1 divided by 2 is 0. Remainder 1. Reading the remainders upward. 1, 1, 0, 1. So 13 in decimal is 1101 in binary. Check your work by expanding. 8 plus 4 plus 0 plus 1 equals 13. Always verify. One critical exam concept is the relationship between the number of bits and the number of values they can represent. With 1 bit, you can represent 2 values, 0 and 1. With 2 bits, you can represent 4 values. With 8 bits, 1 byte, you can represent 2 to the 8th power, which is 256 different values. The general rule is that n bits can represent 2 to the n power distinct values. This comes up in MCQs about storage, color, and data representation throughout the course, so lock that formula in. Hexadecimal is shorthand for binary. Hexadecimal, or hex, is base 16. Here's why it matters. Binary numbers get unwieldy fast. A single byte already needs 8 digits of ones and zeros. Hexadecimal is essentially a compact shorthand that programmers and computer scientists use to represent binary data more readably. Hex uses 16 digits, 0 through 9, and then A through F, where A equals 10, B equals 11, C equals 12, D equals 13, E equals 14, and F equals 15. You need to memorize this mapping cold for the exam. The beautiful thing about hex is its relationship to binary. Since 16 is exactly 2 to the 4th power, every single hexadecimal digit corresponds perfectly to exactly 4 binary digits. This makes conversion between hex and binary almost effortless. To convert binary to hex, simply group the binary digits into chunks of 4 from the right, padding with zeros on the left if needed, and then replace each group of 4 with its hex equivalent. For example, take the binary number 10111101111101 equals 8 plus 2 plus 1, which is 11, that's B in hex. The group 1100 equals 8 plus 4, which is 12, that's C in hex. So 10, 11, 1100 in binary is BC in hexadecimal. Elegant, right? Common exam traps and how to avoid them. Here's where students lose points. The most frequent trap involves leading zeros. The binary number 0101 and the binary number 101 represent the same value, 5, but when you're grouping for hex conversion, those leading zeros matter for keeping your groups aligned. Always pad to complete 4-bit groups. Another trap, students confuse the number of bits with the number of values. 8 bits represents 256 values, ranging from 0 to 255, not 0 to 256. The highest value with n bits is always 2 to the n-1, because 0 is included in the count. If an MCQ asks for the maximum value stored in a byte, the answer is 255, not 256. Students also frequently mix up the direction when doing decimal to binary conversion. They read the remainders in the wrong order and get a reversed answer. Always read remainders from last to first, bottom to top. Connections across the course. Number base knowledge threads through multiple units in AP CSP. In Unit 2, you'll use binary directly when discussing how images are stored as pixels and how color values are represented. The RGB color model uses 3 values, each stored in 1 byte, which is why each color channel ranges from 0 to 255. Hexadecimal colors, like FF5733 in web design, are literally just 3 hex pairs representing red, green, and blue values. In Unit 3, when you work with data and storage capacity, your understanding of bits and bytes drives every calculation. In Unit 5, when you explore the Internet, IP addresses and network protocols all rely on this same binary foundation. Number bases aren't a side topic, they're the skeleton the whole course hangs on. With your understanding of how computers represent numbers firmly in place, you're perfectly set up to explore the next logical question. How do computers represent everything else? Text, images, sound, and beyond? 2.3 Representing text, ASCII, and Unicode. The core problem. How does a computer store a letter? Let's start with a fundamental question that trips up a surprising number of students on test day. How does your computer actually store the letter A? You might already know that computers work in binary ones and zeros, but text isn't a number, so what's going on under the hood? Here's the analogy I love to use. Imagine you and a friend are sending secret messages, but you can only communicate using numbers. You'd need a code book, an agreed-upon table that says 1 means A, 2 means B, 3 means C, and so on. That code book is essentially what ASCII is. ASCII stands for the American Standard Code for Information Interchange, and it's exactly that. A shared agreement between all computers about which binary number corresponds to which character. Without a shared standard, your computer and mine would be speaking completely different languages, and the word hello sent from one machine might show up as gibberish on another. ASCII, the original codebook. ASCII was developed in the 1960s and uses 7 bits to represent each character. 7 bits gives you 2 to the power of 7 possible combinations, which equals 128 unique values numbered 0 through 127. That's enough room for all 26 uppercase letters, all 26 lowercase letters, the digits 0 through 9, common punctuation marks, and a set of special control characters like the new line or tab. Now here's something the AP exam loves to test. Notice that lowercase a and uppercase a are completely different characters with different binary codes. In ASCII, uppercase A is 65 and lowercase a is 97. This is not a coincidence. There are exactly 32 values between them, which in binary is a single-bit flip. But more importantly for you, the exam wants you to understand that the computer treats them as entirely separate symbols. When a program compares A to A, those are not equal values because their binary representations are different. This is one of the most common traps on multiple choice. A question might describe a program searching for uppercase letters and ask whether it would correctly identify a lowercase version of the same letter. The answer is no, because they have different ASCII codes. The formula you need to internalize is this. Number of bits determines number of possible values, and that formula is 2 to the power of n, where n is the number of bits. With 7 bits, you get 128 values. With 8 bits, you get 256. With 16 bits, you get 65,536. The AP exam will give you scenarios where you need to determine whether a given encoding has enough bits to represent a certain number of symbols, and this formula is your whole toolkit for those questions. If someone asks you whether 7 bits is enough to represent 200 different characters, you calculate 2 to the 7th equals 128, which is less than 200, so the answer is no. You'd need at least 8 bits to get 256 possible values. Unicode, opening the codebook to the world. Here's where the story gets interesting. ASCII worked beautifully for English speakers. But what about someone typing in Chinese, Arabic, Hindi, or Greek? ASCII has no room for those characters. In fact, it barely had room for accented characters common in French or Spanish. The world needed a bigger codebook, and that's exactly what Unicode is. Unicode is a universal character encoding standard designed to represent text in virtually every writing system on Earth. Think of ASCII as a small-town diner menu with 128 items, and Unicode as a massive international food court with over 143,000 entries and counting. Unicode currently supports more than 143,000 characters across more than 150 scripts. including emoji. Yes, emoji are Unicode characters too, which is a fun fact the exam might use to make a question feel more accessible. The key conceptual point College Board wants you to understand is this. Unicode is a superset of ASCII. The first 128 Unicode code points are identical to ASCII, so if you encode the letter A in ASCII, it maps to the same value in Unicode. This backward compatibility was intentional and important. It meant that existing ASCII text didn't become obsolete overnight. Why this matters for data and storage. Here's where this topic connects directly to other units you'll see on the exam. In Unit 2, you're also learning about how all data is represented in binary, and text encoding is one of the clearest examples of that principle in action. Every character you type is ultimately stored as a sequence of bits. When you open a text file, your computer looks at those bits and uses the agreed-upon encoding standard to translate them back into human-readable characters. This also connects to the concept of data size and storage, which appears in later questions about the Internet and file transmission. A plain text file with 1,000 characters encoded in ASCII takes up roughly 1,000 bytes, 1 byte per character, since ASCII fits in 7 bits and we typically store it in an 8-bit byte. Unicode encoding formats like UTF-8 are more complex. Common ASCII characters still use 1 byte, but characters outside the ASCII range use 2, 3, or even 4 bytes. The AP exam won't ask you to calculate UTF-8 byte sequences specifically, but it will expect you to understand that different encodings can affect how much storage text requires. The MCQ traps you must avoid. 2 traps show up constantly. The first is confusing the number of bits with the number of possible values. If a question says a system uses 8 bits per character, the number of characters it can represent is 2 to the 8th, which is 256, not 8, not 16, not some other number. Always apply that 2 to the n formula. The second trap is assuming that changing the encoding of a file changes its meaning. It doesn't. The underlying information is the same, but if you read an ASCII file with a Unicode decoder or vice versa, you might get garbled output. The data isn't corrupted, it's just being misinterpreted because the code book being used doesn't match the one used to write it. Exam questions sometimes describe this scenario and ask what went wrong. The answer is always a mismatch between the encoding used to write the data and the encoding used to read it. One more thing to keep in your back pocket. Text representation connects to the broader AP theme that all digital data, text, images, sound, video, is ultimately bits, and the meaning of those bits depends entirely on how we agree to interpret them. That interpretive layer is the encoding standard. With text firmly in your toolkit, you're perfectly positioned to explore how computers represent other kinds of data, including the colors and pixels that make up digital images, which is exactly where we're headed next. 2.4 Representing images, pixels, and color, RGB. Imagine you're standing in front of a giant mosaic, one of those beautiful tile artworks you might see on the floor of a cathedral or subway station. From a distance, you see a perfect image of a landscape or a portrait. But as you walk closer, you start to see the individual tiles. Each tile is a single, flat color. The image isn't actually smooth at all. It's a grid of tiny colored squares, and your brain just does the blending for you when you step back. That mosaic is exactly how every digital image on every screen you've ever looked at actually works. Welcome to the world of pixels. What is a pixel and why does it matter? The word pixel is short for picture element, and it is the fundamental building block of any digital image. Think of your screen as that mosaic, a grid of thousands or millions of tiny squares, each one capable of displaying exactly one color at any given moment. A standard 1080p HD screen, for example, is 1920 pixels wide and 1080 pixels tall, giving you over 2 million individual tiles working together to create the moving pictures you watch. For the AP exam, you need to understand that a pixel is the smallest unit of a digital image and that images are represented as a 2-dimensional grid of these pixels. Now, here's where it gets interesting. How does a computer actually store the color of each one of those tiny squares? This is where the RGB color model comes in, and this is the heart of what the AP exam wants you to understand. The RGB color model, RGB stands for red, green, and blue. These are the three primary colors of light, not paint, not crayon, but light. If you've ever been to a concert and watched colored spotlights combine on a white wall, you've seen this in action. Shine a red light and a green light on the same spot, and you get yellow. Add blue to that, and you get white. This is called additive color mixing because you're adding light waves together. A computer represents every color on your screen by mixing these three channels. Each channel, red, green, and blue, is given a numeric value that represents its intensity, and that's the piece you absolutely must lock in for the exam. Each channel is stored using 8 bits, which gives it a range of values from 0 to 255. 0 means that color channel is completely off, no contribution at all. 255 means that channel is blazing at full intensity. So a pure red pixel would be stored as red, 255, green, 0, blue, 0. Pure white, all channels at maximum, is red, 255, green, 255, blue, 255. Pure black, all channels off, is red, 0, green, 0, blue. And if you set all three channels to the same middle value, say 128, 128, you get a medium gray. The symmetry there is worth noting. Grays always have equal R, G, and B values. The math you must know. Here's the formula chain that ties everything together, and you'll want to have this cold for the exam. Each color channel uses 8 bits, so there are 2 to the power of 8 possible values per channel. That's 256 values, ranging from 0 to 255. Since a single pixel has 3 channels, the total number of bits needed to store 1 pixel is 8 plus 8 plus 8 equals DI as dash ich-reeled 24 bits per pixel. This is why you'll sometimes hear the term 24-bit color or true color. It refers to this exact standard. Now, how many distinct colors is that system capable of representing? You have 256 possible values for red, 256 for green, and 256 for blue. Multiply them together. 256 times 256 times 256 equals Nishnarls. That's over 16 million unique colors from just 3 numbers between 0 and 255 on an MCQ. If they give you any variation of this, say, a system that uses 4 bits per channel instead of 8, you apply the same logic. 2 to the 4 equals 16 values per channel. 16 times 16 times 16 is equal to 4,096 possible colors, and 4 plus 4 plus 4 is equal to 12 bits per pixel. The pattern holds every time. To find the total storage size of an image, multiply the number of pixels by the bits per pixel. A 100 by 100 pixel image has 10,000 pixels. At 24 bits per pixel, that's 240,000 bits of raw data. Watch for this calculation on the exam. They may give you the answer in bytes, so remember to divide by 8. Common traps and misconceptions. The most common MCQ trap is confusing the number of values with the maximum value. 8 bits gives you 256 possible values, but those values run from 0 to 255, not 1 to 256, and not 0 to 256. The maximum value is always 2 to the power of minus 1, where n is the number of bits. A pixel channel set to 255 is at maximum intensity, but 256 would be out of range and impossible in an 8-bit system. If an MCQ gives you a scenario where a channel value exceeds 255, that's a signal something is wrong in the logic being described. Another trap involves mixing up additive and subtractive color. RGB is additive, adding all 3 at full intensity gives white. Subtractive color, like mixing paints, works the opposite way and is not the AP CSP model. Stick with additive for anything involving screens and digital images. Students also frequently mix up resolution and image quality in vague terms when the exam wants precise language. Higher resolution means more pixels in the image, which means more detail, but it also means more data storage required. More bits per pixel means more possible colors, richer color depth, but again, more storage. These are 2 separate axes of image quality, and the exam will test whether you can distinguish them. Connections to other units. This topic connects directly to Unit 2's broader theme of how data is stored and the trade-offs involved in that storage. The same bit depth reasoning you use here, more bits means more possible values, applies to how numbers, text, and audio are represented. It also feeds directly into discussions of data compression in later sections, where you'll see how images can be made smaller by reducing color depth or resolution, and what information is lost or preserved in that process. The concept of metadata, additional stored information about a file, including its dimensions and color depth, also connects here and appears in FRQ context. Understanding that images are just grids of numbers is also foundational for understanding how programs manipulate images. Changing brightness means adjusting all channel values uniformly. Filtering means changing specific channel values. And every Instagram filter you've ever used is ultimately doing arithmetic on those 3 numbers per pixel. With the mechanics of how images, numbers, and text are all encoded at bits firmly under your belt, you're perfectly set up to explore what happens when that data gets too large, and how compression lets us store and transmit it efficiently without always sacrificing quality. 2.5 Representing sound and analog versus digital data. The world in waves. Imagine you're sitting at a cafe and someone at the next table is playing a guitar. What you're actually hearing is air molecules being pushed and pulled in waves, a continuous, smooth, flowing signal that rises and falls like the surface of the ocean. That continuous signal is what we call analog data, and it's how the physical world naturally works. Sound, light, temperature, pressure, all of these exist as smooth, unbroken waves with infinite possible values between any 2 points. Now here's the challenge your computer faces. It doesn't speak the language of smooth waves, it only understands 2 things, on and off, 1 and 0. So before your laptop can store, process, or share that guitar melody, something fundamental has to happen. The analog world has to be translated into the digital world. That translation process is the heart of what this section is all about, and the AP exam is going to test whether you truly understand what gets gained and what gets lost in that translation. Analog versus digital, the core distinction. Let's lock down the vocabulary the College Board uses, because precision matters here. Analog data is data represented by a continuously changing physical quantity, like the voltage in an old telephone wire that rises and falls to mirror the sound of your voice. There are theoretically infinite values possible along the wave, any real number within a range. Digital data, by contrast, is data represented as a sequence of discrete values, almost always in binary. Instead of infinite possibilities, you're working with a finite set of distinct steps. Think of it this way. Analog is like a ramp, smooth, continuous, every height possible. Digital is like a staircase, you can only stand on a step, never between them. The staircase can have more steps, making it approximate the ramp more closely, but it will never perfectly match it. That gap between the ramp and the staircase, that's what we call loss, and it's one of the most important concepts for the exam. How sound gets digitized, sampling. When engineers want to convert analog sound into digital data, they use a process called sampling. Here's how it works. Imagine you're looking at a sound wave drawn on a graph. Time runs left to right along the horizontal axis, and the amplitude or loudness of the wave moves up and down on the vertical axis. The wave is smooth and continuous. To digitize it, you take a snapshot of the wave's height at regular time intervals. Each snapshot is called a sample. The sampling rate tells you how many samples you take per second, measured in hertz, or kilohertz, kilohertz. A sampling rate of 44,100 Hz, the standard for CD quality audio, means you're taking 44,100 little snapshots of the wave every single second. If you were to draw this on a graph, you'd mark tiny vertical measurements at evenly spaced intervals along the wave. The closer those intervals are to each other, that is, the higher your sampling rate, the more accurately your staircase approximates the original ramp. Now, each of those sample measurements also needs to be rounded to the nearest available digital value. The precision of that rounding depends on bit depth, also called the number of bits per sample. If you have 8 bits per sample, you have 2 to the power of 8, or 256, possible values to describe the wave's height. With 16 bits, you have 65,536 possible steps. More bits means a finer staircase, which means a more faithful digital representation. For the exam, remember this relationship. More bits per sample means higher quality, but also larger file size. What gets lost and why it matters? Here's the critical insight the AP exam wants you to internalize. Digitizing analog data always involves some loss of information. No matter how high your sampling rate or how deep your bit depth, you are always approximating. The original analog signal had infinite resolution. Your digital version has finite resolution. This is called lossy representation when the loss is significant and intentional, like in compressed MP3 files. But even so-called lossless digital audio is still an approximation of the original analog wave. It just preserves all the sampled data without further compression. A common exam trap here is the idea that if you use a high enough sampling rate, the digital version becomes identical to the analog original. It doesn't. It becomes a very good approximation, but mathematically and conceptually, perfect reproduction is impossible. The College Board wants you to know that approximation is inherent to the process. The trade-off triangle: quality, file size, and fidelity. For the exam, you need to understand a three-way trade-off. Increasing the sampling rate increases audio fidelity, but it also increases the amount of data you're storing. Increasing the bit depth does the same. If you double the sampling rate, you're storing roughly twice as much data. If you add 1 bit of depth, you double the number of possible amplitude values. The file size grows, and at some point in transmission or storage, that matters enormously. This connects directly to Unit 2's broader themes about data compression and trade-offs, which you'll see in sections 2.3 and 2.4. The decision about how to represent data always involves a balance between accuracy and efficiency. Connections to other units. This topic doesn't live in isolation. Understanding analog to digital conversion helps you later when the course covers the Internet in Unit 4. Data sent across a network is digital, which is exactly why we need this conversion process in the first place. It also connects to the concept of data abstraction. When you digitize sound, you are abstracting a complex physical reality into a simplified numerical model. And in Unit 6, when you consider algorithms, the efficiency of processing audio data depends on how much data you're working with, which circles right back to sampling rate and bit depth decisions. Exam critical distinctions to lock in. Before you move on, make sure these are crystal clear. Analog means continuous and infinite values. Digital means discrete, finite steps. Sampling rate is about how often you measure. Higher means better time resolution. Bit depth is about how precisely you measure each sample. More bits means better amplitude resolution. And no matter what you do, converting analog to digital always produces an approximation, never a perfect copy. Students frequently confuse sampling rate with bit depth on the multiple choice section. So keep those two dimensions separate in your mind. One is about time, the other is about precision of measurement. With a solid grasp of how sound and physical phenomena get translated into the ones and zeros a computer can use, you're perfectly positioned to tackle the next concept: how we compress all that data down so it doesn't overwhelm our storage systems and networks. 2.6 Limitations of data representation. Overflow. Round-off error. The fundamental problem: fitting infinity into a finite box. Here's a thought experiment for you. Imagine trying to pour the ocean into a coffee cup. No matter how carefully you pour, no matter how precisely you aim, something gets left out. That's essentially the situation computers find themselves in every single time they try to store a number. The universe of numbers is infinite, stretching endlessly in both directions with infinite decimal places between any 2 points. But computer memory is stubbornly, unforgivingly finite. Every number a computer stores has to fit inside a fixed number of bits, and that constraint produces two of the most important limitations you need to know for the AP exam: overflow errors, and round-off errors. These aren't exotic edge cases that only matter to aerospace engineers. They're fundamental. They appear regularly on the AP-CSP exam, and understanding them deeply is what separates a 3 from a 5. Overflow error. When numbers get too big for the container, let's start with overflow. Every data type in a computer program has a fixed number of bits allocated to store its values. Think of those bits like the digits on an old mechanical odometer in a car, one of those satisfying rolling number displays. An odometer with 6 digits can display anything from 0,000,000 to 9999999. But what happens when you hit 9999999 and the car keeps rolling? The odometer wraps around to 0000. There, the car has traveled 1,000,000 miles. But the display says 0. That's overflow. In computing, when a calculation produces a result that's larger than the maximum value the allocated bits can represent, you get an overflow error. For the AP exam, College Board defines overflow as the condition that occurs when a program computes a value that is outside the range of values representable in a given number of bits. The result doesn't just get capped at the maximum, it wraps around or produces a completely wrong value. That's what makes overflow genuinely dangerous. You don't get an obviously absurd answer like infinity. You get a number that looks plausible but is completely wrong. Here's a concrete example. Suppose a program uses 4 bits to store a non-negative integer. With 4 bits, you can represent 2 to the power of 4, which gives you 16 possible values, 0 through 15. If you try to store the result of 12 plus 5 is equal to 17, that 17 doesn't fit. In binary, 17 is 1001, which requires 5 bits. The leading 1 gets dropped, leaving 0001, which is 1. Your program just told you that 12 plus 5 equals 1. You can see how this becomes catastrophic in financial software, navigation systems, or anything safety critical. For the AP exam, the key formula to internalize is this. With n bits, you can represent 2 to the n distinct values. If you're representing non-negative integers, that's 0 through 2 to the n minus 1. If that maximum value is exceeded, overflow occurs. You will almost certainly see an MCQ that gives you a number of bits and asks you to identify whether a specific calculation causes overflow. So practice working out 2 to the n quickly for small values of n. A critical exam trap here is confusing overflow with just getting a wrong answer for other reasons. Overflow specifically means the value exceeded the representable range due to the fixed bit constraint. Keep that definition precise in your mind. Round-off error, when precision gets trimmed. Now let's talk about the other side of this problem, not numbers that are too large, but numbers that are too precise. Round-off error occurs when a number cannot be represented exactly in the available bits and must be approximated. This is especially common with decimal numbers. Think about trying to write the fraction 1/3 using only a finite number of decimal digits. You could write 0.3 or 0.3333, but no matter how many 3's you write, you never get exactly 1/3. You have to stop somewhere and accept an approximation. Computers face this exact problem with certain decimal values because they store numbers in binary, and many perfectly clean decimal fractions like 0.1, for example, have no exact binary representation. They become infinitely repeating binary fractions, and since memory is finite, they get cut off and rounded. The practical consequence is that arithmetic in computers can accumulate small errors. If you add 0.1 to itself 10 times in a program, you might not get exactly 1.0. You might get 0.99999999999 or 1.0000000 Darlow 8 or nine or 1.0000000 star loot 0.000000000 line 999999999
9999999999999.
The College Board wants you to understand that round-off error is unavoidable when storing numbers that cannot be represented exactly in binary with a fixed bit width. A common MCQ trap is presenting a scenario where a program produces a slightly wrong decimal answer and asking you to identify the cause. The distractor answer will often suggest the programmer made an error in the code. The correct answer will recognize it as round-off error arising from the limitations of binary representation. Connecting these concepts across units, these limitations connect beautifully to other parts of the course. In Unit 2 overall, you've been building an understanding of how data of all kinds, numbers, text, images, sound, gets encoded in binary. Overflow and round-off are the natural consequence of that encoding when the data doesn't fit cleanly. When you get to Unit 4 and start thinking about algorithms and programming, you'll see these errors become relevant in loop conditions, counter variables, and calculations involving floating point numbers. Anytime a program processes numerical data, the potential for these errors lurks in the background. There's also a connection to the broader AP-CSP concept of the digital divide and the limitations of computing in general. Computers are extraordinarily powerful, but they are not mathematically perfect. This is a philosophical point the exam loves to test. Computing systems can introduce errors simply by virtue of how they represent information, independent of any programming mistake. What to memorize and watch for. For the exam, make sure you can do 3 things confidently. First, given a number of bits, n, calculate the maximum representable non-negative integer as 2 to the n minus 1, and identify whether a given value causes overflow. Second, recognize round-off error as the result of representing a number that has no exact binary equivalent, and understand that repeated arithmetic operations can accumulate this error. Third, distinguish clearly between the two. Overflow happens when a number is too large for the allocated bits, while round-off happens when a number can't be represented exactly regardless of its size. With these limitations firmly in your toolkit, you're ready to move forward into how computer scientists and programmers work around these constraints, which leads us directly into the world of abstraction and problem-solving strategies that define the next sections of this course. 2.7 Data Compression. Let's talk about something you do every single day without realizing it. You compress data. When you send a voice memo instead of typing out a long paragraph, when you zip up a folder before emailing it, when you stream a movie without downloading 30 gigabytes first, that's all data compression at work. And for the AP exam, College Board wants you to understand why it exists, how it works, conceptually, and this is the critical part, the crucial difference between its 2 major flavors. Why compression exists. Think about your closet. If you just throw everything in randomly, you run out of space fast. But if you fold things neatly, use vacuum storage bags, and organize by category, suddenly you can fit twice as much. Data compression does the same thing for digital storage and transmission. Every file, a photo, a song, a video, is ultimately a string of bits, and compression is the art of representing that same information or approximately the same information using fewer bits. Here's the key concept. College Board wants you to nail compression, reduces the number of bits needed to represent data, which means files take up less storage space and can be transmitted faster across a network. That second point matters, bandwidth. The amount of data you can send per second is finite and often expensive. Compression helps you send more faster using less. This is why compression connects directly to Unit 4 content on the internet and data transmission. When you're thinking about why protocols and streaming services exist in their current form, compression is part of that answer. Lossless compression. Now let's get to the heart of this topic, because this is where College Board loves to test you. There are exactly 2 types of compression you need to know: lossless and lossly. Lossless compression is like a perfect filing system. You take the original data, compress it, and when you uncompress it, you get back exactly what you started with. Not a single bit has changed. The original data is perfectly reconstructed. Here's a vivid way to think about it. Imagine you have a sentence that says, UB, ABBCC. Instead of storing 11 characters, you could store a shorthand like 6A, 3B, 2C, which takes up way less space. When you decode it later, you get back exactly UB, ABBCC. Nothing was lost. You just got cleverer about representation. This technique is called run-length encoding, and it's a classic example College Board uses to illustrate lossless compression. Another real-world lossless format you should know? Zip files. When you zip a folder, your computer finds patterns and redundancies in the data and represents them more efficiently, and when you unzip, you get the originals back perfectly. Text files, spreadsheets, and executable programs are almost always compressed losslessly because even a single changed bit could corrupt a program or change a meaning. The AP exam will ask you to identify when lossless compression is appropriate. The answer is whenever the exact original data must be preserved. Think legal documents, medical records, source code, financial data. No approximation is acceptable. Lossy compression. Now here's where things get interesting and where most students make mistakes on the exam. Lossy compression deliberately throws away some data to achieve much higher compression ratios. You cannot recover the original data after lossy compression. That information is gone permanently. Think about how your ears work. When you listen to a song, there are certain frequencies, very high pitches, very quiet sounds buried under louder ones that you basically can't hear. MP3 compression exploits this. It analyzes the audio, identifies sounds the human auditory system is unlikely to notice, discards that data, and stores only what you'll actually perceive. The result? A file that might be 10 times smaller than the original, and to most listeners, sounds nearly identical. JPEG images work the same way with visual data. Your eyes are less sensitive to subtle color variations in busy or textured regions of an image, so JPEG discards some of that color detail. That's why if you keep resaving a JPEG over and over, it gets blurrier. You're applying lossy compression repeatedly, discarding a little more data each time. This is a real boundary condition to remember. Lossy compression applied multiple times causes cumulative degradation. Each save throws away more of the original. Common formats to associate with each type for the AP exam. Lossless includes PNG, GIF, FLAC, and ZIP. Lossy includes JPEG, MP3, and MP4 video. You don't need to memorize codec specifications, but you should be able to look at a scenario and classify it correctly. The critical trade-off and common exam traps. Here's the trade-off College Board wants you to state clearly. Lossless compression preserves all original data, but typically achieves lower compression ratios, meaning the resulting file is still relatively large. Lossy compression achieves much higher compression ratios, much smaller files, but at the cost of some data fidelity. Now let me flag the most dangerous wrong answer trap on this topic. Students often read a question and think, lossy compression is always worse because it loses data. That's not the right frame. Lossy compression is better for appropriate use cases. Streaming video, music distribution, photo sharing, because the data loss is imperceptible and the file size savings are enormous. The exam will test whether you understand that choosing the right type of compression is context dependent. If a question describes a hospital storing MRI scans, you should think lossless. If it describes a music streaming service, you should think lossy is fine. Another trap. Students sometimes say that compression is about changing the data. It isn't. It's about changing the representation of the data to use fewer bits. For lossless compression, the underlying information is identical, only the encoding has changed. You should also know that there is a theoretical limit to how much any lossless algorithm can compress data. This connects to information theory. Random data, like truly random noise, cannot be compressed at all because there are no patterns to exploit. This is an edge case that shows up in MCQs. If someone claims a lossless algorithm can compress any file, that claim is false. Some files will not get smaller, or may even appear to get slightly larger after a compression attempt. Connecting it all together. This topic ties beautifully to other units. In Unit 2, you've already thought about how numbers, text, and images are represented in binary. Compression is the next logical step. asking how you can represent the same information more efficiently. In Unit 4, when you study the internet and data transmission, compression is one of the key reasons massive amounts of data can travel across networks quickly enough to feel instantaneous. And in Unit 5, when you think about the impacts of computing, consider that compression technologies are part of what made streaming services, social media, and cloud storage economically and technically feasible for billions of people. Next, we move into Unit 3, where all that data you've been storing and compressing starts doing something, because now we're going to talk about how algorithms actually process and manipulate information to solve problems. 2.8 Lossless versus lossy compression. Why compression matters in the first place. Let's start with a scenario you already understand intuitively. Imagine you're trying to fit everything you own into a moving truck that's half the size you need. You have two options. You can carefully fold and stack things to use every inch of space efficiently without throwing anything away. Or you can toss out the stuff you probably won't miss. The box of old magazines, the extra kitchen gadgets, the furniture that's just a little worn. Both strategies get you into the smaller truck, but one of them means you're not getting everything back. That's the essential difference between lossless and lossy compression, and it's the heart of everything College Board wants you to know in this section. Compression exists because data takes up space, and space, whether on a hard drive, in memory, or flying across a network, costs time and money. When we compress data, we're using an algorithm to represent the same information in fewer bits. The AP exam will test whether you understand not just what compression does, but which kind is appropriate and why the trade-off exists. Lossless compression, getting everything back. Lossless compression reduces the size of a file in a way that allows the exact original data to be perfectly reconstructed. Every single bit you started with can be recovered. College Board's official language here is important. With lossless compression, the original data can be reconstructed from the compressed data. No information is lost, hence the name. Think about how a zip file works. When you zip a folder of text documents and later unzip them, every word, every comma, every space is exactly where it was before. The compression worked by finding patterns and redundancies. Maybe the word "the" appeared 400 times in a document, and the algorithm replaced each instance with a shorter code. When you decompress, the algorithm reverses that substitution and gives you back "the" every single time. This is lossless. Run-length encoding is a classic example the AP exam loves. If you have a sequence of data like AB, BC, CC, instead of storing all 13 characters, you store 6A, 3B, 4C. You've captured the same information in far fewer characters, and you can reconstruct the original perfectly. That's the conceptual model of lossless compression. Exploit redundancy without discarding anything. Lossless compression is critical when the data cannot tolerate even a single changed bit. Text files, executable programs, spreadsheets, databases, these all require lossless compression. If even one character in a spreadsheet formula or one byte in a program's instructions gets altered during compression and decompression, the whole thing might break or produce wrong results. The AP exam will often present scenarios and ask which type of compression is appropriate. Anytime you see data that must be reproduced exactly, lossless is your answer. Lossy compression, accepting the trade-off. Lossy compression takes a different approach entirely. It achieves much greater reductions in file size by permanently discarding some data, specifically data that a human being is unlikely to notice is missing. The key phrase from College Board is this: with lossy compression, data is lost and cannot be recovered. Once you compress using a lossy method and save the file, the original is gone. There is no way to get back exactly what you started with. Here's where your brain probably says, "Wait, why would anyone want that?" The answer is perception. Consider an audio file of a song. The full, uncompressed audio might contain frequencies that only dogs can hear, subtle background hiss below human detection thresholds, and thousands of variations in tone that your ear blends together anyway. The MP3 format strips out those imperceptible elements. The file becomes a fraction of the size, and when you listen to it, it sounds to most human ears essentially identical to the original. You've lost data, but you haven't lost an experience you could perceive. That's the genius of lossy compression. JPEG images for photographs work the same way. A photograph of a sunset has thousands of nearly identical shades of orange blurring into each other. JPEG compression approximates those subtle gradations rather than storing every exact pixel value. The resulting file can be 10 times smaller, and you look at it on your phone and think it looks fine. But the math tells a different story. The pixel values are not the same as the original. That information is permanently gone. This also explains why you should never use lossy compression on text, code, or numeric data. If a JPEG algorithm slightly alters a character in a text document, the letter O might become the number 0. If a single digit in a financial record gets rounded or approximated, the data is corrupted. The exam will test this boundary precisely. The core trade-off and what College Board emphasizes. Here's the central principle you need to nail down. Lossy compression achieves smaller file sizes than lossless compression for the same source file, but at the cost of permanent data loss. Lossless compression preserves all data but typically achieves more modest reductions in size. The appropriate choice always depends on the type of data and how it will be used. A classic MCQ trap is suggesting that lossy compression is universally inferior because it loses data. It isn't for images, audio, and video shared over the internet. Lossy compression is often the correct and preferred choice. Another trap involves the word quality. The AP exam might describe a compressed image as having reduced quality, and you need to connect that language specifically to lossy compression, because quality reduction is the signature of data being discarded, not just reorganized. You should also be comfortable with the idea that compressing a file multiple times using lossy compression compounds the damage. Each time you save a JPEG as a JPEG, it loses a little more data. After several rounds of this, the degradation becomes visible. That characteristic blurry, blocky appearance is called compression artifact. The exam may describe this kind of accumulated degradation. Connections to other units. This topic connects directly to the broader Unit 2 themes of how data is stored and transmitted. You've already learned that all data is represented in bits, and that the number of bits determines the precision of that representation. Compression is essentially about reducing the number of bits used, lossless. Does it without sacrifice. Lossy does it by accepting approximation. This also ties into the Internet and network units later in the course, where bandwidth limitations make compression a practical necessity for streaming video and audio. When you study the Internet, remember that the efficiency of data transmission depends on compression choices made right here in Unit 2. One more distinction to lock in. Students sometimes confuse compression with encryption, since both transform data into something that looks different from the original. They are completely separate processes. Compression reduces file size. Encryption protects data from unauthorized access. You can compress, then encrypt, or encrypt, then compress. They serve different purposes. Don't let a tricky question conflate them. With compression firmly in your toolkit, you're ready to zoom out and look at the bigger picture of how all this data, compressed or not, moves across the systems and networks that make modern computing possible. 2.9 Metadata and its uses. What metadata actually is. Let's talk about something that surrounds you every single day. Even though you almost never think about it, metadata. Here's the best way to picture it. Imagine you take a photo on your phone. The photo itself, the image of your friend laughing at a party, that's your data. But wrapped around that photo, invisible to you unless you go looking, is a whole second layer of information. When the photo was taken, where you were standing, GPS coordinates, what camera settings were used, what device you took it on, even sometimes who's in it if facial recognition is enabled. That second layer, that's metadata. The College Board's definition is precise, and you should have it memorized. Metadata is data about data. It describes the properties, characteristics, and context of the primary data without being the data itself. This distinction between the data and the data about the data is the conceptual core of this entire section, and it's exactly what the AP exam will test you on. Metadata doesn't change what the data says. It provides context that helps you understand, organize, find, and use the data more effectively. Metadata in everyday digital life. Let's build your intuition with a few more examples before we get into the exam mechanics. Think about a music file, an MP3, sitting on your computer. The audio waveform itself, the actual sound when you press play, that's the data. But the song title, artist name, album, year of release, track number, genre, even the album artwork, all metadata. Your music app uses that metadata to sort your library, build playlists, and display information on your screen. Without it, you'd have thousands of identically labeled files with no way to organize them. Or think about an email. The actual words of the message. Hey, can you meet me at 3 p.m.? That's your data. But the sender's address, the recipient, the timestamp, the subject line, the size of the message, whether it's been read, what folder it's in, that's all metadata. And here's where this gets genuinely important, and where the AP exam loves to go. Metadata can reveal a tremendous amount about you, even when the content of your data is completely private. Intelligence agencies and legal investigators often say that metadata alone can paint an extraordinarily detailed picture of someone's life, who they call, how often, at what hours of the night, from what locations. The content of the call might be encrypted and private, but the metadata surrounding it can still tell a story. Why metadata matters: organization, findability, and privacy. The AP exam tests metadata from two distinct angles that you need to keep cleanly separated in your mind: its utility and its privacy implications. On the utility side, metadata is what makes large-scale data management possible. Think about a hospital with millions of patient files. Without metadata, the file creation date, the patient ID, the doctor who created the record, the type of document, you'd have an unsortable mountain of information. Metadata is what allows search engines, databases, and file systems to locate and retrieve the right piece of data from among billions of options, almost instantly. When Google's search algorithm indexes a web page, it's largely working with metadata: the page title, the description tags, when the page was last updated, what other pages link to it. The metadata is doing enormous organizational work behind the scenes. On the privacy side, and this is where the exam really likes to probe your understanding, metadata collection raises serious concerns. The College Board specifically wants you to recognize that collecting metadata is often less regulated than collecting the actual content of communications, even though metadata can be surprisingly revealing. The scenario you should be ready to analyze on an FRQ goes something like this. Even if a messaging app encrypts the content of messages so no one can read them, a third party who can see the metadata, the timing, frequency, and participants of those messages can potentially infer sensitive personal information. That is not hypothetical. It's a real and active area of debate in technology law and policy. Common MCQ traps and how to dodge them. Let me flag the traps that show up again and again on AP CSP exams so you can step around them confidently. The first trap is confusing metadata with the data itself. A question might describe an image file and ask you what constitutes metadata. Students who haven't internalized the distinction will sometimes circle the pixel color values that make up the image, but that's the data. The correct answer will be something like the date and time the image was captured, or the GPS coordinates where the photo was taken. The rule is simple: if it describes or characterizes the data rather than being the data, it's metadata. The second trap involves the assumption that metadata is harmless because it isn't the real content. The AP exam will present scenarios designed to test whether you understand that metadata can compromise privacy in meaningful ways. If a question tells you that a privacy-conscious user encrypts all of their messages and asks whether their communication patterns are still potentially private, the correct answer acknowledges that metadata, the who, when, and how often, can still be exposed and can still be sensitive. The third trap is scope. Students sometimes think metadata only applies to media files like photos and videos. Not even close. Every type of digital data can have metadata: documents, emails, database records, web pages, spreadsheets, even the files that make up software programs. When the AP exam gives you an unfamiliar scenario, the question to ask yourself is, what information describes this data rather than being the content of this data? Whatever your answer is, that's the metadata. Connections to other units. Metadata doesn't live in isolation. It threads through the entire APCSP course in ways that will help you on the exam if you see the connections. In Unit 3, when you study the way programs store and process data, the structure of metadata in files and databases is directly relevant. In Unit 5, when you tackle the impact of computing on society, the privacy implications of metadata collection connect directly to discussions of surveillance, data brokers, and digital rights. Metadata also connects to the big data concepts earlier in Unit 2. When you have enormous datasets, metadata is often the only practical tool for navigating and analyzing them efficiently. When you think about lossy versus lossless compression, remember that compression algorithms sometimes strip metadata to reduce file size, which means that a compressed image might lose its GPS coordinates and timestamp, even though the visual content is preserved. That's a subtle, exam-worthy consequence of data compression. Tying it together. So here's your mental anchor for metadata. It's the label on the box, not the contents inside. It describes, characterizes, and contextualizes data, making it searchable, organizable, and usable at scale. But it can also tell a story on its own, which gives it real privacy weight. Anytime the AP exam asks you about data and you see information about that data hovering nearby, you're looking at metadata. With our understanding of how data is described and organized now firmly in place, we're ready to push deeper into how data is actually used at scale, which brings us to the powerful and sometimes controversial world of data collection and analysis. 2.10 Extracting information from data. The detective work of computer science. Imagine you walk into a coffee shop every morning for a year and jot down what you order, the time, the weather outside, and how long it took to make your drink. By December, you've got 365 rows of information. Now here's the question: do you have information, or do you just have data? This distinction is at the heart of Section 2.10, and it's one the AP exam absolutely loves to test. Data, on its own, is just raw facts. Numbers, words, timestamps with no meaning attached. Information is what you extract from that data through analysis, visualization, and computation. Your job in this section is to understand how that transformation happens and what tools make it possible. Data, information, and the extraction process. The College Board wants you to be precise about language here. Data refers to the raw values collected. Think of it as the ingredients sitting on a kitchen counter. Information is what you get once you start cooking, patterns, trends, and conclusions drawn from that data. Extracting information means processing data in ways that reveal something meaningful. This might involve filtering, sorting, aggregating, or visualizing the data, and most of the time you'll need a computer to do it efficiently, because humans simply cannot scan a million rows of spreadsheet data and spot a trend with their naked eyes. Computers can. That's the whole premise. The AP exam will ask you to recognize that the same dataset can yield different information depending on how you analyze it. Your coffee shop data, for example, might reveal that wait times spike on Monday mornings. That's one piece of information. It might also reveal that you spend more on lattes when it's raining. That's a completely different piece of information pulled from the exact same rows. Don't fall into the trap of thinking a dataset has only one answer. Multiple valid conclusions can be drawn, and the exam may ask you to evaluate which conclusions are actually supported by the data versus which ones are assumptions. Visualizations, seeing patterns in the numbers. One of the most powerful tools for extracting information is data visualization, turning numbers into pictures. When you graph data, patterns that are completely invisible in a table of numbers suddenly pop out. The AP exam expects you to understand several types of visualizations and what each one is best suited for. A scatter plot is your go-to for exploring the relationship between two numerical variables. Picture two axes. The horizontal axis is your independent variable. The vertical is your dependent variable, and each data point is a dot placed at its coordinates. If the dots trend upward from left to right, you have a positive correlation. As one variable increases, so does the other. If they trend downward, it's a negative correlation. If the dots look like someone threw confetti randomly, there's no correlation at all. Here's a critical AP trap. Correlation does not imply causation. If your scatter plot shows that ice cream sales and drowning rates both rise in summer, that doesn't mean ice cream causes drowning. Both are caused by a third factor, hot weather. Whenever you see a scatter plot on the exam, ask yourself whether the relationship shown is truly causal or just coincidental. A line graph is ideal when you're tracking how something changes over time. The x-axis is time, the y-axis is your measured value, and you connect the data points with a line to show the trend. If you're looking at website traffic month by month, a line graph makes it easy to see whether traffic is growing, shrinking, or staying flat. Bar charts and histograms, meanwhile, are great for comparing categories or showing frequency distributions. The distinction matters. A bar chart has gaps between the bars because the categories are discrete, while a histogram has no gaps because it's showing continuous numerical ranges, called bins. Metadata and its role in understanding data. Here's a concept the AP exam sneaks in that students frequently overlook. Metadata is data about data. When you take a photo on your phone, the image itself is the data, the pixels, the colors, but embedded in that file is metadata. The date and time the photo was taken, your GPS coordinates, the camera settings, the file size. Metadata helps you understand the context of your data. When you're evaluating a dataset on the exam, ask, what does the metadata tell us about how, when, and where this data was collected? That context directly affects whether the data is reliable and what conclusions you can legitimately draw. Cleaning data and handling noise. Real-world data is messy, and the AP exam acknowledges this. Cleaning data means identifying and correcting errors, removing duplicates, handling missing values, and dealing with outliers data points that are dramatically different from the rest. An outlier might be a legitimate extreme value, or it might be a data entry error. Either way, it can distort your analysis if you're not careful. If your coffee shop dataset shows one day where the wait time was 847 minutes, that's almost certainly an error. Someone typed extra digits, and including it in an average would make your results meaningless. The AP exam may also ask about processing limitations. Even with powerful computers, there are constraints. Datasets can be so large that processing them requires distributed computing, spreading the work across many machines simultaneously. This connects directly to Unit 4 concepts around the Internet and parallel computing, where you'll see that breaking a large problem into smaller concurrent tasks can dramatically reduce processing time. Connections across the course. This topic is a hub that connects to almost everything else in AP-CSP. When you write programs in Unit 3 that use lists and iteration, you're building the computational foundation for processing datasets. When Unit 4 discusses how data moves across the Internet and how it's stored, you're seeing where the raw data comes from before extraction begins. And in Unit 5, when you examine the societal impact of computing, you'll confront the ethical dimensions of data analysis: who owns the data, who benefits from the information extracted, and what biases might be baked into the dataset before analysis even starts. A dataset collected only from one demographic group will produce information that doesn't generalize well to everyone, and recognizing that limitation is part of responsible data literacy. The most important exam traps. Let me leave you with 3 traps to tattoo on your brain before exam day. First, more data is not always better. If the data is biased or collected poorly, more of it just amplifies the problem. Second, a tool that visualizes data doesn't automatically extract meaningful information. You have to choose the right visualization for the question you're asking. Third, a strong correlation in a scatter plot is not evidence of causation. This comes up on nearly every practice exam in some form, and it is almost always one of the wrong answer choices dressed up to look reasonable. With your toolkit for extracting information from data now sharp and ready, you're perfectly set up for the next section, where we'll explore how data is actually stored and managed at scale, and what happens when the sheer volume of information pushes the boundaries of what any single system can handle. 2.11 Data Visualization and Interpretation. Why visualization matters. Imagine you're handed a spreadsheet with 10,000 rows of raw numbers, sales figures, temperatures, social media likes, whatever. Your brain glazes over almost immediately, right? That's exactly why data visualization exists. It's the art and science of turning raw data into a picture your brain can actually process. And for the AP exam, College Board doesn't just want you to admire pretty charts. They want you to read them critically, identify what they reveal, and just as importantly, recognize what they hide or distort. That skill is what this section is all about. The core idea, metadata, and what makes data useful. Before we even get to graphs, let's talk about the foundation. Data on its own is just symbols. What gives data meaning is context, and that context is often captured through what College Board calls metadata, which is data about data. Think of metadata as the label on a can of soup. The soup is the data. The label tells you what's inside, when it was made, how much is there, and how to use it. On the exam, you might be asked whether a dataset is useful for answering a specific question, and the answer often hinges on whether the metadata tells you enough to interpret the numbers correctly. If you don't know when the data was collected or how or from whom, you simply can't trust it for many purposes. Types of visualizations. You must know. Now let's walk through the visualizations themselves. The ones College Board cares about most are scatter plots, bar charts, line graphs, and to a lesser extent, infographics. Each one has a specific job. A scatter plot is your go-to tool for showing the relationship between two numerical variables. Picture two axes, one for each variable. Every data point is a dot placed where those two values intersect. If you're studying for the exam, you need to be comfortable reading the overall pattern, called a trend, in a scatter plot. A positive correlation means the dots slope upward, left to right, like how more hours of studying tends to connect with higher exam scores. A negative correlation slopes downward, like how more absences tend to connect with lower grades. And sometimes there's no pattern at all. The dots are scattered randomly, like confetti, which means no correlation. The critical thing the exam tests here is the difference between correlation and causation. Just because two things move together does not mean one causes the other. Ice cream sales and drowning rates both go up in summer. Clearly, it's the heat driving both, not the ice cream. This is one of the most common wrong answer traps on the AP exam, and College Board loves it. If an answer choice says a scatter plot proves one thing causes another, that answer is wrong. Full stop. A bar chart, sometimes called a bar graph, compares categorical data, things like different cities, different app categories, or different months. The height or length of each bar represents a quantity. When you see a bar chart on the exam, your job is to compare the bars accurately and avoid being fooled by a manipulated axis. Here's a classic trap: a bar chart where the y-axis doesn't start at 0. If you're comparing bars that look dramatically different in size, but the axis starts at, say, 97 instead of 0, the visual difference is exaggerated. College Board will absolutely show you a chart like this and ask whether the visualization is misleading. The answer is yes, and the reason is that it distorts the visual representation of the data, even if the underlying numbers are accurate. A line graph is best used when your data involves change over time. It's perfect for showing trends across a continuous variable like months or years. The slope tells you the rate of change. A steep upward slope means rapid increase. A flat line means no change. One edge case the exam loves. What does it mean when a line graph shows data going up, then down, then up again? It means the trend is not consistent, and you should be cautious about making predictions. A common mistake students make is assuming a line graph's direction will continue forever. That's called extrapolation, and it's risky. You can extrapolate carefully with good reason, but the exam will sometimes offer answer choices that over-extrapolate, and those are usually traps. What visualizations can and cannot tell you. Here's a concept that ties everything together. Every visualization is a simplification, and simplifications leave things out. A visualization that shows average salary by job category, for instance, doesn't show you the distribution of salaries within each category. A few extremely high earners could be pulling that average way up. This connects to a broader AP principle. You must evaluate not just what a visualization shows, but what it omits and whether it's the right tool for the question being asked. College Board also expects you to understand that the same dataset can be visualized in multiple ways, and different visualizations can support different, even contradictory conclusions. If someone wants to make a trend look dramatic, they choose a truncated axis and a steep-looking line graph. If they want to downplay the same trend, they zoom out and make it look flat. Being a savvy consumer of data means asking, who made this visualization? What are they trying to show? And is this the most honest representation of the data? That critical lens is very much an AP exam skill. Connections to the rest of the course. Data visualization doesn't live in isolation. It connects directly to Unit 2's earlier lessons on data collection and cleaning. Garbage in, garbage out means a beautiful chart of bad data is still bad data. It also ties into the broader theme of digital information, Unit 1, since all of these visualizations ultimately represent data stored and processed computationally later in the course. When you explore algorithms and program design, you'll see that choosing the right data structure often parallels choosing the right visualization. Both decisions shape what you can and cannot do with your information efficiently. For the free response questions, if you're ever asked to evaluate a data visualization, structure your answer around 3 things: what the visualization shows clearly, what it might obscure or distort, and whether it's appropriate for the question being asked. Examiners reward that structured, critical thinking every time. With a solid understanding of how data gets turned into visual stories, and how those stories can sometimes mislead, you're ready to move into the next major theme: the societal and ethical implications of how we collect, use, and sometimes misuse that data. 2.12 Bias in Data and Algorithms. What bias really means in computer science. Let's start by clearing up something important, because the word bias carries a lot of emotional weight in everyday life. When College Board talks about bias in data and algorithms, they're using it in a precise technical sense. Bias is any systematic error that causes a model, dataset, or algorithm to consistently favor certain outcomes over others in ways that don't reflect reality. Think of it like a bathroom scale that always reads 5 pounds too heavy. It's not random noise, it's a consistent, predictable distortion. That's bias. Now here's why this matters for your exam. The AP exam wants you to understand that bias doesn't just happen because someone had bad intentions. Bias can enter a system at multiple points, and recognizing those entry points is exactly what the multiple choice questions will test you on. Where bias comes from, the 3 entry points. Imagine you're building a spam filter. You train it on emails collected only from one company's servers, and that company happens to be in finance. Your filter is going to be brilliant at catching financial scams and terrible at recognizing scam emails written in other languages or targeting other industries. That's a problem with your training data, and it's the most common source of bias the AP exam will ask about. The first entry point is biased data collection. This happens when the sample used to train or inform an algorithm doesn't represent the full population it's meant to serve. If you survey only people who own smartphones to learn about technology access, you've already excluded the people who don't have smartphones, which skews your results in a predictable, systematic direction. College Board loves to give you scenarios where the sample looks large and impressive, but the method of collection is flawed. Always ask yourself who is missing from this data. The second entry point is human bias encoded in labels and decisions. Lots of machine learning systems learn from historical human decisions, hiring records, loan approvals, medical diagnoses. If those historical decisions reflected human prejudice, the algorithm learns to replicate that prejudice at scale. A hiring algorithm trained on 20 years of a company's hiring history will learn to prefer the kinds of candidates that company historically hired, even if those patterns reflect old biases rather than genuine predictors of job performance. The third entry point is algorithmic design choices. Sometimes the people building the system make choices about which variables to include, how to weight them, what counts as a good outcome that introduce bias. This is subtler but just as consequential. These choices reflect the values and assumptions of the designers. and those assumptions may not apply equally to all users. The impact, why, this isn't just a technical problem. Here's where your exam wants you to think bigger. Biased algorithms don't just make incorrect predictions in the abstract, they can cause real, unequal harm to people. This connects directly to the beneficial and harmful effects of computing themes that run throughout the AP course. Consider facial recognition technology. Studies have shown that some systems have significantly higher error rates for darker-skinned faces in women compared to lighter-skinned men, largely because the training datasets overrepresented certain demographics. If that technology is used in law enforcement or hiring, the errors are not distributed equally across the population. Certain groups bear a disproportionate burden of the system's mistakes. That's the critical leap the AP exam wants you to make. Bias in data leads to bias in outputs, which can lead to unequal treatment of people in the real world. This topic connects directly to Unit 5's focus on the impact of computing on society, and to your understanding of crowdsourcing and data collection in earlier sections of Unit 2. When you think about large data sets and why more data doesn't automatically mean better or fairer data, you're drawing on exactly this concept. Recognizing and reducing bias. The AP exam will also ask you about strategies for identifying and mitigating bias. So let's walk through the key ideas. First, you need diverse and representative datasets. If you're building a medical diagnostic tool meant for all patients, your training data needs to reflect the actual diversity of patients, different ages, ethnicities, biological sexes, geographic regions, and so on. A dataset that's technically large but systematically missing groups is still biased. Second, you need human oversight and audit. Algorithms should be evaluated not just for overall accuracy, but for whether their accuracy is consistent across different subgroups. If your spam filter is 95% accurate overall, but only 60% accurate for emails written in Spanish, that's a bias problem hiding behind a good headline number. The AP exam might describe a situation where a system performs well on average, but underperforms for a specific group. Recognize that as bias, not just normal variation. Third, there's the concept of being transparent about limitations. A system that's been trained on data from urban environments should disclose that limitation if it's going to be deployed in rural areas. Acknowledging what a dataset doesn't include is part of responsible computing practice. The MCQ traps you need to avoid. Here's the most dangerous wrong answer trap on this topic: the idea that larger datasets automatically eliminate bias. They do not. If your data collection method is flawed, collecting more data using that same flawed method just gives you more of the same bias. The exam will offer you an answer choice that says something like the bias could be reduced by collecting more data, and it's tempting because more data sounds better. But if the collection method itself is skewed, more data won't fix the problem, it will entrench it. The second trap is confusing random error with bias. Random errors go in unpredictable directions and can cancel each other out. Bias is systematic, it consistently pushes outcomes in one direction. An algorithm that sometimes overpredicts and sometimes underpredicts for everyone has random error. An algorithm that consistently overpredicts for one group and underpredicts for another has bias. Know that distinction cold. A third trap is assuming that removing obviously sensitive variables like race or gender from a dataset eliminates bias. This is sometimes called the fairness through blindness fallacy. If your dataset contains other variables like zip code or school attended that are strongly correlated with race or gender, the algorithm can still learn to discriminate based on those proxy variables, even without seeing the sensitive variable directly. Connecting the dots, remember that bias in data and algorithms sits at the intersection of technical understanding and ethical responsibility, which is exactly why College Board includes it in this course. When you see a question on your AP exam about computing's impact on society, or about the responsibilities of developers, or about evaluating the reliability of a dataset, bias is almost certainly part of the answer. Keep asking yourself who collected this data, how was it collected, who is missing, and whose outcomes are affected by the errors. As we move forward into exploring the broader societal impacts of computing, and the legal and ethical responsibilities that come with building powerful systems, you'll see that everything we've discussed about bias is really just the foundation of a much bigger conversation about what it means to build technology that serves everyone equitably. 2.13. Using programs with data. The big picture: why programs and data go together. Imagine you're working at a coffee shop and every morning you jot down how many lattes, cappuccinos, and drip coffees you sell. After a week, those numbers are just a pile of tallies on a napkin, but the moment you plug them into a spreadsheet, sort them, find the average, and make a little bar chart, suddenly you have insight. You know which drink to stock up on, which one to stop making at 2 p.m., and when your rush hours hit, that transformation from raw numbers to meaningful understanding is exactly what this section is about. Using programs with data means leveraging computational tools to turn raw, unprocessed information into something actionable. The College Board's core idea here is straightforward but profound. Programs can be written to process data, and that processing reveals patterns and draws conclusions that would be impossible, or at least wildly impractical, to find by hand. This is the philosophical foundation of the entire data unit, so make sure it's crystal clear in your mind. What counts as using a program with data? On the AP exam, you need to understand that using a program with data involves several interrelated actions: collecting data, storing it, transforming it through algorithms, and then presenting or analyzing the results. Think of these as 4 links in a chain. If any link breaks, the whole process fails. The College Board wants you to recognize that computational tools, meaning programs, scripts, spreadsheets, even automated systems, allow humans to work with datasets far too large or complex for manual analysis. Here's an analogy that will stick with you. Imagine you have 1 million survey responses about high school lunch preferences. Even if you had a team of 50 people, manually counting and cross-referencing those results would take weeks and introduce errors constantly. A program can do it in seconds, perfectly. That's the why behind this topic. Computational tools extend human capability. They don't replace thinking, but they massively amplify it. Cleaning, transforming, and processing data. One of the most exam-critical concepts in this section is the idea that data must often be cleaned and transformed before it can be used. Raw data collected from the real world is messy. Values might be missing, recorded inconsistently, or formatted differently across sources. A program can filter out incomplete records, standardize units, remove duplicates, and otherwise make data usable. On the multiple choice section, you'll frequently see questions that describe a dataset with issues and ask you what kind of processing step would address the problem. Recognize these keywords. Filtering means selecting only records that meet a condition. Sorting means ordering data by some attribute. And aggregating means combining values, like summing or averaging a column. The most common trap on MCQs here is confusing cleaning data with analyzing it. Cleaning is preparation. Analysis is the actual process of drawing conclusions. If a question describes removing rows where age is listed as 0 and asks what kind of operation this is, the answer is cleaning or filtering, not analysis. Don't let the word process blur those 2 distinct stages in your head. Visualizing data. Graphs you must know. The AP exam will absolutely test your ability to interpret data visualizations, and Section 2.13 connects directly to that skill. The key graphs and models you need to understand are scatter plots, bar charts, line graphs, and frequency tables. Let's walk through each one briefly. A scatter plot displays 2 numerical variables, one on each axis, and places a dot for each data point. When you see a scatter plot on the exam, your job is to identify trends. Is there a positive correlation? Dots trend upward, left to right. A negative correlation? Dots trend downward, or no correlation at all. A common wrong answer trap is assuming that correlation implies causation. Just because 2 variables move together does not mean one causes the other. The College Board loves to test this. Be vigilant. A bar chart uses rectangular bars to compare categories. Each bar's height represents a quantity, and the categories are usually labeled on the horizontal axis. When interpreting bar charts, look at relative heights to compare categories and absolute heights to read actual values. A line graph shows change over time, with the horizontal axis typically representing time and the vertical axis representing the measured value. Line graphs are great for spotting trends and identifying when dramatic changes occurred. A frequency table organizes data into categories and shows how many items fall into each one. These are the raw material for many charts. On the FRQ section, if you're ever asked to describe what a visualization shows, use precise language. Say, the frequency of X increases as Y increases, rather than vague phrases like, it goes up. Programs that generate insights. Here's where it gets exciting. The whole point of processing data with a program is to move from raw values to genuine understanding. Programs can calculate statistics mean, median, mode, range, which summarize large data sets with single numbers. They can also identify outliers, which are data points that fall far outside the typical range. Outliers matter enormously on the exam because they can skew means significantly, making the median a better measure of center in some cases. Picture it this way. If 9 students score between 70 and 85 on a quiz, and 1 student scores a 4, the mean gets dragged way down by that single outlier. The median, on the other hand, barely budges. Understanding when to use, which measure of center, and why, is a key decision rule for this section. Use the mean when data is symmetric and lacks outliers. Use the median when data is skewed or contains outliers. Connections to other units and FRQ scoring. This section doesn't exist in isolation. It connects directly forward to Section 2.14 on data compression and backward to 2.1 through 2.5 on binary and data representation. It also links to Unit 1 concepts around abstractions, because summarizing 1 million data points into a single average is itself an act of abstraction. On the FRQ, when you're asked to describe how a program uses data, you earn points by explicitly naming the operations, filter, sort, aggregate, explaining what each operation does to the data, and stating what conclusion or insight the result provides. Vague answers like, the program looks at the data, earn nothing. Precise answers like the program filters records where age is less than 18, then calculates the average score for the remaining records, earn full credit. The most important habit to develop for this entire section is thinking in terms of input, process, output. What data comes in, what operations transform it, what result or insight comes out. If you frame every question that way, you'll find the right answer almost every time. Coming up next, we'll look at how data is stored more efficiently through compression techniques, and you'll see exactly how the ideas from this section about representing and processing data feed directly into making those storage decisions. 2.14 Collaboration and Tools in Data Analysis. Why? You can't do data science alone. Imagine you're trying to assemble a 1,000-piece puzzle, but you've been blindfolded and can only touch 10 pieces at a time. That's what analyzing large, complex datasets looks like when you try to go it alone with a single tool and a single perspective. The College Board knows this, and that's exactly why collaboration and the intelligent use of tools are woven right into the AP-CSP framework, not as soft skills fluff, but as genuine computational practices that affect how good your analysis actually is. Let's talk about what the exam actually wants you to understand here and why it matters beyond test day. Collaboration as a computational practice. The AP exam treats collaboration not as a nice-to-have, but as a core part of the problem-solving process. Think about how scientists actually work. They share data, challenge each other's interpretations, and combine expertise. A biologist, a statistician, and a computer scientist looking at the same genomic dataset will each catch something the others miss. That diversity of perspective is the whole point. For the exam, you need to know that collaboration and data analysis means more than just dividing up tasks. It means combining different areas of expertise to improve the quality of the analysis itself. One person might be great at writing queries to pull data from a database, while another has the domain knowledge to know whether the results even make sense. Neither person alone produces as reliable an outcome as both working together. This is the College Board's concept of combining diverse talents and perspectives, and it shows up on MCQs framed around why collaborative teams produce better computational artifacts. A common trap on the multiple choice section is a question that asks why collaboration is valuable in data analysis, and one of the wrong answers will say something like, "It makes the work go faster." Speed is a side benefit, not the core reason. The correct answer will almost always center on the idea that multiple perspectives reduce bias, catch errors, and improve the quality of conclusions drawn from data. Watch for that distinction. Tools for data analysis. What you need to know. The exam expects you to understand that different tools exist for different stages and scales of data work, and that choosing the right tool is itself a computational decision. Think of tools on a spectrum. At the accessible end, you have spreadsheet software. Think Microsoft Excel or Google Sheets. These are fantastic for small to medium data sets where you can visually inspect the data, create charts, run basic statistical functions, and share your work with collaborators easily. If your data set fits on a screen and your analysis involves things like finding averages, sorting values, or making a bar chart, a spreadsheet is perfectly appropriate. The exam might describe a scenario where a student is analyzing survey results from 200 classmates. A spreadsheet is the right call there. But now imagine you're working with millions of records. Say, every purchase made on an e-commerce platform over 5 years. A spreadsheet buckles under that weight. This is where computational tools like programming languages and database systems become essential. Python, R, and structured query languages like SQL allow analysts to manipulate, filter, aggregate, and visualize data at a scale no human could manage manually. You don't need to write SQL for the AP exam, but you absolutely need to understand conceptually that these tools exist to handle large datasets that exceed what manual or spreadsheet-based analysis can manage. This distinction, the right tool for the scale and complexity of the problem, is a concept the College Board tests directly. Expect a scenario question where you have to identify which type of tool is most appropriate. If the dataset is described as extremely large or containing millions of records, the answer will involve automated computational tools, not a spreadsheet. Visualization as a collaborative communication tool. Here's where things get interesting for the exam. Data visualization isn't just pretty pictures, it's a communication tool that makes complex data accessible to collaborators and stakeholders who may not be technical experts. When you create a well-labeled scatter plot or a histogram, you're translating raw numbers into a form that enables collaboration and shared understanding. The exam will ask you to interpret visualizations, so let's make sure you know what to look for. A scatter plot shows the relationship between two variables. You're looking for a correlation, clusters, or outliers. If the dots trend upward from left to right, that's a positive correlation. Downward trend means negative correlation. Dots scattered with no discernible pattern suggest little to no correlation. Remember, and this is a critical exam point, correlation does not imply causation. This phrase might as well be tattooed on the AP-CSP exam. Two variables moving together does not mean one is causing the other. Ice cream sales and drowning rates both rise in summer, but ice cream doesn't cause drowning. Hot weather causes both. Histograms show you the distribution of a single variable, how frequently values appear across ranges. A bar chart compares categories. These are different, and the exam knows students confuse them. A histogram has no gaps between bars because the data is continuous. A bar chart has gaps because the categories are discrete. If you see a question describing a visualization of test score ranges across a class, that's a histogram. A visualization comparing the number of students in each grade level, that's a bar chart. Cleaning and preparing data, the unglamorous reality. Another key concept the College Board tests here is that raw data is almost never ready to analyze directly. Real-world data has missing values, duplicate entries, formatting inconsistencies, and outliers that can skew your results dramatically. Collaboration is especially valuable at this stage because different team members might notice different quality issues. The process of identifying and correcting these problems is called data cleaning, and it's a prerequisite to meaningful analysis on the FRQ section. If you're asked to describe a data analysis process, always mention data cleaning as a step between collection and analysis. Scoring rubrics often have a point allocated specifically for acknowledging that raw data requires preparation before it can be used reliably. Connecting to the rest of the course. This topic ties directly to Unit 5, where you'll revisit how programming can automate data processing tasks, and to the broader theme of beneficial and harmful effects of computing, because poorly analyzed data, whether from inadequate tools or working in isolation, can lead to flawed decisions that affect real people. It also connects to the performance task, where you'll demonstrate your ability to work with data and potentially collaborate on design decisions. The big takeaway here is elegantly simple. Good data analysis requires the right tools, the right team, and the right critical eye for what the data is actually telling you versus what you want it to say. Up next, we'll push deeper into the ways data can be visualized and what those visualizations reveal and conceal about the patterns hiding in plain sight. 2.15 Combining and Cleaning Datasets. Why raw data is like a grocery haul before dinner. Imagine you just got home from 3 different grocery stores. You've got bags from Whole Foods, Trader Joe's, and a local farmer's market, and everything is just dumped on the counter. Some produce has stickers with prices, some doesn't. You've got duplicates of things you didn't need. One bag has a bruised apple that'll ruin the fruit salad if it gets in. Before you can cook anything useful, you have to sort, combine, and clean that haul. Data works exactly the same way. In the real world, data almost never arrives neat and ready to analyze. It arrives messy, scattered, and incomplete. And your job as a data-aware citizen, and as someone prepping for the AP exam, is to understand what it means to prepare that data properly. This is exactly what Section 2.15 is about. The processes of combining multiple datasets and cleaning data so it's actually useful for analysis. Let's walk through every piece you need to know. What it means to combine datasets. When researchers, companies, or governments want to answer complex questions, they rarely have everything they need in one place. Combining data sets means merging data from 2 or more sources into a single unified collection. Think about a public health researcher studying the relationship between fast food restaurant density and childhood obesity rates across a state. They might pull restaurant location data from one government database, health outcome data from hospital records, and demographic information from census data. None of those sources alone can answer the question. Only when combined do the patterns become visible. For the AP exam, you need to understand that combining datasets introduces real challenges. The most important one is compatibility. If one dataset measures income in dollars and another measures it in thousands of dollars, combining them without adjusting will produce completely distorted results. If one hospital system records patient ages as ranges, like 18 to 25, and another records exact ages, those fields can't simply be merged without making a deliberate decision about how to handle the mismatch. College Board loves to test whether you recognize that a combined dataset is only as useful as the care taken to align its components. Another key challenge is identifying a common attribute that links the 2 datasets, something like a shared ID number, a zip code, or a date. Without a linking field, you can't meaningfully join 2 tables together on the exam. You might see a scenario where 2 datasets both contain a student ID column, and the question asks what that allows you to do. The answer is that it allows you to combine records from both sets that belong to the same individual, a process sometimes called joining or merging. What it means to clean data. Data cleaning, sometimes called data cleansing or preprocessing, is the process of identifying and correcting problems in a dataset before analysis begins. This is one of those topics where the College Board expects both conceptual understanding and awareness of the specific types of errors that occur. The most common data issues you need to know for the exam are incomplete data, inaccurate data, and redundant data. Incomplete data means missing values, a survey where some respondents left questions blank, or a sensor that failed to record for part of a day. Inaccurate data means values that are just wrong, a user who typed their age as 999, a temperature reading of -500 degrees Celsius, or a zip code with letters in it. Redundant data means duplicates, the same record entered twice, which would skew any average or count you calculated. Here's a real-world analogy that makes this click. Imagine you're calculating the average test score for a class of 30 students, but 3 students submitted their scores twice by accident, and 2 entries show a score of 0 because the system recorded absences as zeros rather than leaving them blank. If you just dump that raw data into a calculator, your average is going to be meaningfully wrong. Cleaning means you remove the duplicates, decide how to handle the absences, exclude them, record as missing, assign a 0, and only then run your analysis. That decision point, how to handle missing or invalid data, is something the AP exam tests explicitly. You should know that there is no single correct answer, but you do need to understand the trade-offs. Deleting rows with missing values reduces your sample size. Replacing missing values with an average, called imputation, preserves sample size but introduces artificial data. Either choice affects the conclusions you can draw, and acknowledging that limitation is part of responsible data practice. Common MCQ traps and how to dodge them. The biggest trap on this topic is assuming that more data automatically means better analysis. A combined dataset with incompatible formats, mismatched units, or duplicate entries can produce conclusions that are worse than a smaller, cleaner, single-source dataset. If an exam question suggests that combining 2 large datasets will always improve the reliability of results, that is a trap. The answer hinges on whether the data was properly cleaned and aligned. Another common wrong answer choice involves treating data cleaning as optional or cosmetic. The exam wants you to recognize that unclean data leads to invalid conclusions, not just slightly off ones, but potentially completely backwards ones. If you calculate the median income of a neighborhood and half the entries are duplicates, skewing toward high earners, your median no longer represents the typical resident at all. Watch out also for questions that conflate combining data sets with simply collecting more data from the same source. These are different things. Combining means bringing together data from distinct origins, which introduces compatibility concerns that collecting more from one source does not. Connections to the rest of the course. This topic sits at the heart of Unit 2's bigger argument. The data is only as powerful as the process used to collect, organize, and interpret it. It connects directly backward to 2.3 on extracting information from data, because you can't extract reliable information from a poorly combined or uncleaned dataset. It connects forward to the big idea of data and analysis throughout the course, and it underpins your ability to think critically about any data-driven claim you encounter, including in the Explore Performance task. It also connects to Unit 4's discussion of algorithms, because cleaning and combining datasets is itself an algorithmic process. Someone had to design the rules for how duplicates get removed, how missing values get flagged, and how 2 tables get joined. Those rules matter enormously. Most importantly, this topic is a cornerstone of the AP exam's broader theme of responsible computing. Whenever you see a question about whether a model or conclusion is trustworthy, ask yourself, do you know where this data came from? Has it been properly combined? And has it been cleaned? If the answer to any of those is no, then the conclusion deserves skepticism. With a solid understanding of how raw data gets transformed into something analytically useful, you're ready to think about how we actually visualize and interpret that data, which is exactly where we're headed next. 2.16 Privacy and Security Concerns with Data Collection. The digital footprint you didn't know you were leaving. Let's start with a thought experiment. This morning, before you even got out of bed, how many devices knew you were awake? Your phone probably tracked when you first unlocked it. Your smartwatch logged your heart rate transitioning from sleep to wakefulness. Maybe a smart speaker heard you groan at your alarm. By the time you made it to school, dozens of data points had already been collected about you, and you hadn't done anything unusual at all. That's the world we're living in, and it's exactly what this section of the AP exam is all about. The College Board wants you to understand 2 intertwined ideas here. First, that data collection creates genuine privacy risks, and second, that the same data infrastructure that creates convenience also creates vulnerability. Let's unpack both of those. What the exam means by personally identifiable information. The term you absolutely must know cold is personally identifiable information, or PII. The College Board defines PII as any information that can be used to identify an individual. This includes the obvious stuff, your name, social security number, home address, phone number, but here's where students trip up on multiple choice questions. PII also includes information that seems harmless in isolation, but becomes identifying when combined with other data. Your zip code alone doesn't identify you. Your birthday alone doesn't either. But your zip code plus your birthday plus your gender. Research has shown that combination uniquely identifies a surprisingly large percentage of the U.S. population. This concept is called data aggregation, and it's a favorite topic on the AP exam. Think of it like a jigsaw puzzle. One puzzle piece tells you almost nothing, but you keep snapping pieces together and suddenly a recognizable picture emerges. The trap on MCQs is when the exam describes data that seems anonymous and asks whether it constitutes a privacy risk. The answer is almost always yes, if that data can be combined with other sources to re-identify someone. Don't let the word anonymous fool you. Context matters enormously. The tension between convenience and privacy. Here's an analogy I love. Giving your data to a company is like giving a spare key to a neighbor. You do it because you trust them and it's convenient. But once that key exists, you've lost some control over who might eventually use it. The neighbor might move. The key might get copied. You might forget you gave it out in the first place. This is the core tension the AP exam wants you to articulate. Digital systems collect data to improve services, personalize experiences, and generate revenue. Search engines remember your queries to serve better results. Social media platforms track your engagement to show you relevant content. Navigation apps log your location to predict traffic. In every case, you get something useful, and in every case, you surrender something private. The exam will ask you to evaluate whether a particular trade-off is acceptable, and the right approach is always to acknowledge both sides rather than dismissing either the benefit or the risk. The College Board specifically wants you to know that metadata, data about data, can be just as revealing as the content itself. A text message's content might be private, but the metadata, who you texted, when, how often, from where, paints a remarkably detailed picture of your life. Law enforcement agencies and intelligence services have long understood this, and the exam tests whether you do too. Security, threats, and how they connect to privacy. Now let's shift from privacy to security, because the exam treats these as connected but distinct. Security concerns focus on protecting data from unauthorized access, while privacy concerns focus on whether data should be collected and how it should be used in the first place. You need to keep that distinction sharp. The major security threats the AP exam expects you to know are phishing, malware, and unauthorized access through weak authentication. Phishing is a social engineering attack where someone tricks you into revealing credentials or clicking malicious links by posing as a trustworthy entity. Think a fake email from your bank asking you to verify your account. Malware is malicious software which includes viruses, ransomware, and spyware designed to damage systems or steal information without the user's knowledge. These connect directly back to privacy because a successful malware attack often results in personal data being exfiltrated and sold on dark web marketplaces. One concept that bridges security and privacy beautifully for the exam is encryption. When data is encrypted, it's transformed into a format that's unreadable without the proper key. This protects privacy by ensuring that even if data is intercepted during transmission or stolen from a server, it remains meaningless to the attacker. The AP exam connects encryption to the idea of the Internet's architecture. Data travels across many devices before reaching its destination, and without encryption, any node along that path could read your information. This is why HTTPS matters, why end-to-end encrypted messaging apps are significant, and why encryption is considered a fundamental privacy protection rather than just a technical nicety. Legal and ethical dimensions. The College Board also expects you to understand that laws and policies attempt to address privacy concerns and that they don't always succeed. Laws like COPPA, Children's Online Privacy Protection Act, restrict data collection on users under 13. FERPA protects student educational records. HIPAA governs medical information. The exam won't ask you to memorize the details of these statutes, but it will present scenarios and ask you to reason about whether a particular data practice raises ethical or legal concerns. The key principle is informed consent. Individuals should know what data is being collected, why, and who it's being shared with. When that knowledge is absent or buried in a 1,000-word terms of service agreement that nobody reads, the ethical standard of informed consent is arguably not being met. Connecting to other units. This topic doesn't live in isolation on the exam. It connects directly to Unit 5 when you study the impact of computing on society. Everything you learn here about privacy trade-offs resurfaces in discussions about computing's benefits and harms. It also connects to the earlier sections of Unit 2 about how data is stored, compressed, and transmitted, because understanding data's technical life cycle helps you reason about where vulnerabilities emerge. And when you study cybersecurity more formally, you'll find that the foundational vocabulary you're building right now, PII, metadata, encryption, phishing, becomes the language for every subsequent conversation. The deeper truth that ties all of this together is simple: data has power. The entity that holds data about you holds a form of influence over you, whether through targeted advertising, credit decisions, or government surveillance. Understanding those power dynamics isn't paranoia. It's exactly the kind of informed, critical digital citizenship the AP exam is trying to cultivate in you. With that foundation in place, let's move forward and look at how computing innovations continue to reshape our world in ways both beneficial and challenging.